Okay, welcome to 2008 Form B. This is question number 6, a 10-point thermodynamics question. So the question says a 0.0040 mole sample of a monatomic gas is taken through the cycle as shown above. The temperature T1 of state 1 is 300 Kelvin. So if you look, we have an equilateral triangle. Not equilateral. We have a right triangle here. Position 1 is here. It goes up to position 2, down to position 3, and then it becomes completely reversible, which means it goes back to position 1 to start the cycle all over again. And there's information on the graph that we're going to use. I've put my givens over here on the right, and they will be on each slide. Okay, so let's take a look and see what they want us to find out. Part A says calculate T2 and T3. Well, in order to find the temperature at one point, you have to reference it with another. And a really easy way to do that is by using the ideal gas law. And the ideal gas law says P1 V1 over T1 equals P2 V2 over T2. Now, if you look, the difference between 1 and 2, obviously we know a lot of information about 1. It tells us the temperature at 1, so we're going to use 1 as our known. If you look at 2, the volume between 1 and 2, this right here, that's isochoric. The volume stays constant. Well, if volume stays constant, we can get rid of the volumes because they're the same. So now we just have P1 over T1 equals P2 over T2, and you simply replace. So I know the pressure at point 1 is given. You can see it down here as 100 times 10 to the third. The temperature measured in Kelvin is 300. The pressure at point 2 is also listed right down here. It's 500, and I forgot this should be 500 times 10 to the third right here, Pascal. So that goes right here. Over top of T2, which is what we're looking for. And when you go through and calculate it out, you find the temperature at point 2 is going to be equal to 1,500 Kelvin. And now what we're going to do is we're going to find the temperature at 3. Well, you're going to do the same thing. You want to pick something you know about. So you can either pick 1 or 2 at this point, but let's just stick with 1, and we're going to use the ideal gas law again. Now looking at this, I have my position that I'm going from is 1 to 3. So I'm looking at this right now, that part right there. So what stays the same between 1 and 3? Well, looking, I've got right here my 1 and 3, the pressure stays the same. So that disappears out of the equation, and now it's a simple plug and chug situation. The volume at point 1, which is right here, is listed as 1 times 10 to the negative 4th. The temperature at 1 remains 300. The volume at 3 is 6 times 10 to the negative 4th. And T3 is our unknown. And when you go through and solve it, you find that the temperature at point 3 is 1,800 Kelvin. All right, part B says calculate the amount of work done on the gas in one cycle. Now you can use the equation that work is equal to negative P delta V. However, what I would like to do is use the relationship that work is the area enclosed. Now what area enclosed am I talking about? That would be this area in here. Anything enclosed. That doesn't mean everything underneath of it. If you want to find the work done for a particular cycle, that would be the area underneath of it. But because you see that this is going in this direction and this is going in this direction, we're actually going to subtract the areas. So if you want to find the work done during a complete process, you want to find the blue area in there. Well, if you want to find the area of a triangle, it's 1/2 base times height. So if you plug in your values for the triangle, you end up calculating that you should get about 100 joules. So if you're not entirely certain how to do that, there are a couple ways to do that. But the easiest, like I said, is just to use 1/2 BH. When you plug in your values, area is equal to 1/2. The base in this case would be this, which is a difference of 6 down to 1, which is 5 times 10 to the negative 4th, times my height, which is this, which is a difference of 400 times 10 to the 3rd. And when you multiply this out, you find out that your area is 100 joules, therefore that must be the work. Okay, the next part says, is the net work done on the gas in one cycle positive, negative, or 0? Well, in this case, if you look at your setup, you've got two different areas. You've got the area under this curve, which goes all the way down, okay? That is going to the right. This part, only this part, is going to the left. Well, the general rule is, and you can use the equations to prove this, but once again, it's much easier to just know the rule, is that if right is bigger than left, that means it's negative work. So that means the arrow going to the right was bigger than the arrow, or the area under the arrow going to the left, therefore this must be negative work. And for the very last part, it says calculate the heat added to the gas during the process from 1 to 2. Well, if you look at the process from 1 to 2, right here, you'll notice that there is no work being done. So in our equation, there is no work being done, therefore we can just forget that ever existed. So if I can find delta U, I can find Q. Well, there's only one equation you have for delta U. And finally, we get to use all those given pieces of information they gave us. So 3/2, N is given as 0.004, R is 8.31. And now we need to look at this temperature. Well, the temperature right here is the change in temperature. Well, we found from part A, the temperature at 2 was 1500. So this becomes final, which is 1500 minus 300. And once you plug all that into your calculator, you should find you get 60 joules.